everyone. I am in group 2 with Dap, Doma, Jorge, Mario L, and myself, Mario HM. And our project deals with the curve of pursuit. So from this text, a simple explanation would be an interesting geometric model arises when one tries to determine the path of a pursuer chasing its prey. This path is called a curve of pursuit. These problems were analyzed using methods of calculus circa 1730, more than 2 centuries after Leonardo da Vinci had considered them. The simplest problem is to find a curve along which a vessel moves in pursuing another vessel that flees along a straight line, assuming the speeds of the two vessels are constant. So from the given problem, let's assume that vessel A, traveling at speed alpha, is pursuing vessel B, which is traveling at speed beta. In addition, assume that vessel A begins at time t equals 0 at the origin and pursues vessel B, which begins at the point 1, 0, and travels up the line x equal to 1. After t hours, vessel A is located at the point p equals xy, and vessel B is located at the point q 1 equals 1, beta t. The goal is to describe the locus points of P, that is, to find y as a function of x. So in conclusion, our project deals with calculating the pursuit of vessel A onto vessel B.
Perfect. So we start off with part A, and part A asks us if vessel A is pursuing vessel B. So at time t, vessel A must be heading right at vessel B. That is, the tangent line, which will be important to us, to the curve of pursuit at P must pass through the point Q. For this to be true, show that dy over dx equals y minus beta t over x minus 1. So to solve this problem, we know that a to b is a slope function, basic y2 minus y1 over x2 minus x1. And we can see that y1 is bt from q, x1 is 1. So all we have to do is plug it into the slope equation. And the question also gives us that tangent line. So we know that tangent theta equals dy over dx, or the difference in y over the difference in x, which is the same as tangent theta equals y minus beta t over x minus 1. And if we substitute tangent theta dy dx into the equation, we can see that dy over dx equals y minus beta t over x minus 1, which is what they asked us to find.
Moving on to part B, we know that the speed at which vessel A is traveling, so we know that the distance it travels in time t. The distance is also the length of pursuit curve from 0, 0 to xy, using the arc length formula from calculus. And then we have our equations. We have 5 to solve, and then comes also we need 6 to solve by solving for the t equations for 4 and 5 that conclude that. And by using parts A's graph, we can find and know what to do to determine the length of the continuous function y of fx on the interval of 0 and pi. Initially, we will need to estimate the length of the curve. We will do that by dividing the interval in n equal to subinterval, each of the width of triangle pi, and we will denote the point on the curve by pi we can approximate the curve as a series of straight lines. By that, we have the length equals 2 to pi I minus pi I, and we can use that by getting the exact length as n to infinity. Now, having that and using that on our limit, and having n to infinity and to I to on the length, we can continue to evaluate and do the equation. And with that, we will be using the bi-mean value theorem on the interview for that, where the a point of xi so that the equation can be broken down to its length right here, as you can see shown in the right hand side of my work. And regarding to the next equation, we use our equation over here for 4. We have t equals y minus x minus 1 over b. So we substitute that on right. We substitute that with the equation of 5, and then boom, we get our answer right here as our final answer by using the table and using the equation for 4 and 5 as seen as shown on the work on the right hand side. Thank you.
Part C asks to differentiate both sides of equation 6, found in the previous step B, with respect to x using the substitution w equals the derivative of y with respect to x. In order to do this, first multiply both sides of equation 6 by beta in order to remove beta from the left-hand side. Next, break off the left-hand side and derive with respect to x. Then you can split the second term according to the power rule. For step 2, simplify the expanded terms. After subtracting like terms, the left-hand side is successfully reduced. For the right-hand side, the differentiation and integration cancel. Rewrite the y prime found in the body of the integral in Leibniz notation. Set both sides equal to each other and multiply both sides by -1. Using the given substitution of dw equals dy dx, this results in the desired equation stated at the beginning of the problem.
It asks me, using separation of variables and the initial conditions x equals to 0 and w equals dy over dx equals to 0 when t equals to 0. Show that with those initial conditions, we end up with this equation here. So from a previous part, which would be part C, in this part we end up with this given equation, which I am going to use for my part, which is right here, which is x minus 1 times dw over dx equals to negative beta over alpha square root 1 plus w to the second power. So here I'm going to use this given differential equation, and it looks like it's separable. So I'm going to solve this knowing that beta and alpha are constants. So from here I would separate this differential equation and then take the integral of both sides. Solving for both sides, I will end up with ln values, and from here down I would use ln definitions to further simplify this equation all the way up until I get about to this point here. After taking the integral and simplifying it, I will end up with this equation w equals 1/2 parentheses c parentheses 1 minus x. Well, pretty much this equation here. Now once I get to this point, my problem gives me initial conditions where x is equal to 0 and w is also equal to 0. Now, using these given values, I plug them in into this equation that I got from this first differential equation, and as I solve, plugging in the values for 0, I end up with c is equal to -1. Now, using this given value for c, I then go back to this equation and plug in the values for c. Once I plug in the values for c, you could determine that this equation here, this final equation, is the same equation that I got myself from solving this initial equation. So this is part of the process of calculating for this next equation, which is part E, which is not my part, but from my equation, you derive the curve of pursuit, which is for this part.
Hello everyone, my name is Mario Lingajaya, and now let's do part E. So for part E, it's given that for A larger than B, which is pursuing puzzle A is faster than pursuit interval B. So we're gonna use the previous equation with the initial condition x equals 0, y equals 0, when z equals 0, to derive the curve of pursuit. So this is the curve of pursuit, and now we're gonna use the previous equation to basically find it. So what we're gonna do now is we get the equation from part D, which is w equals to 1/2 times -1 minus x to the power of beta over alpha plus 1 minus x to the power of negative beta over alpha. And we can rewrite this equation as w equals 1/2 times 1 minus x to the power of negative beta over alpha minus 1 minus x to the power of beta over alpha. And this equation would equals to dy over dx. Now we can rewrite this equation on the differential equation form, where dy is equals to 1/2 times 1 minus x over 1 minus x to the power of negative beta over alpha minus 1 minus x to the power of beta over alpha dx. Now we can find the general solution of this differential equation by integrating both sides, where we differentiate dy and we also differentiate the other side. We know the differential of dy is y, and now we can solve the other side, where we can basically substitute 1 minus x with t, dx with minus dt, and this means that minus dx is dt. So this would give us y equals to the integral of minus 1/2 times t to the power of beta over alpha minus t to the power of beta over alpha dt. And we can also rewrite this equation to y equals into the integral of 1/2 times t to the power of beta over alpha minus t to the power of negative beta over alpha dt. So since we know that the integral of t to the power of n is equals to t to the power of n plus 1 over n plus 1, we can solve this integral. So this means that the equation becomes y equals to 1/2 times t to the power of 1 plus beta over alpha over 1 plus beta over alpha minus t to the power of 1 minus beta over alpha over 1 minus beta over alpha plus a constant. And now we can substitute t with the previous substitution, which is t equals 1 minus x, and it becomes this equation. Right. Now, from the initial condition, which is x equals to 0, y equals to 0 when t is equals to 0, we can plug in the initial condition to find the constant of this equation. So from here, we know that 0 is equals to 1/2 times 1 minus 0 to the power of 1 plus beta over alpha, which will equals to 1 over 1 plus beta over alpha, minus 1 minus 0 to the power of 1 minus beta over alpha, which also equals to 1 over 1 minus beta over alpha plus c. And now from this equation, we know that the result of c is equals to negative 1 over 2 times 1 over 1 plus beta over alpha minus 1 over 1 minus beta over alpha. And now we can simplify or rewrite this equation as c equals to negative 1 over 2 times alpha over alpha plus beta minus alpha over alpha minus beta. And now we can cross multiply this equation, and this would give us c equals to negative 1 over 2 times c times c, sorry, so c equals to negative 1 over 2 times alpha minus beta minus alpha times alpha plus beta over alpha plus beta times alpha minus beta. And this would give us c equals to negative 1 over 2 times negative 2 alpha times beta over alpha squared minus beta squared. And from this, we understand that the constant of this equation, or c, would equals to alpha times beta over alpha squared minus beta squared. And now we can input back the previous equation, or the general solution, which gives us y equals to 1 over 2 times 1 minus x to the power of 1 plus beta over alpha over 1 plus beta over alpha minus 1 minus x to the power of 1 minus beta over alpha over 1 minus beta over alpha plus alpha times beta over alpha times beta over alpha squared minus beta squared. And this is the curve of pursuit as indicated by the question. And now we have proven that we can derive the equation from previous part to find the curve of pursuit. And that's part F. Thank you.
It asks you find the location where vessel A intercepts vessel B if alpha is greater than beta. So in order for vessel A to intercept B, as it is shown here, it has to be greater than B, or else it won't never reach B. So from the previous part, using this equation, which is the curve of pursuit, I am giving the initial value here, x is equal to 1, and plugging in x equal to 1 to the curve of pursuit equation, I get the value y equals this value here. Now, this is where vessel A intercepts B, which is 1 comma beta times alpha over alpha squared minus b squared. And this given coordinate is where A intercepts B.
Great. So now that we're on our last part of the question, part G says, show that if alpha equals beta, then the curve of pursuit is given by y equals 1 over 2 bracket 1 over 2 bracket parentheses 1 minus x parentheses squared minus 1 bracket minus ln parentheses 1 minus x. And it also asks us, will vessel A ever reach vessel B? So for the solution is, we know that alpha equals beta, and from part D we found this equation. And since alpha equals beta, we can substitute it into the exponential part right here, and we get negative 1 and 1. And then we integrate on both sides, integrate y prime and integrate this function. We get y equals 1/2 bracket minus ln absolute value 1 minus x plus 1/2 x squared. With a better algebra, we can see that our final answer is what they ask us to find. Lastly, will vessel A ever reach vessel B? No, it will not. How? We can find it by plugging in x equals 1 into this equation, and we see that y will approach infinity. Therefore, A will never reach B.